All right, in this video we're going to talk about quadratic-like functions. Okay, so functions that can be written in quadratic form, and then we will also talk about multiplicity. Okay, so an equation that is written in quadratic form, it can be rewritten as a quadratic in standard form. Okay, so think about something like x to the fourth minus 25x squared plus 144. We could kind of think of this as x squared squared minus 25 x squared plus 144, right? And then just like, do you guys see how this is really just a quadratic? It's some variable being squared minus 25 times a variable. What's important here is that those x squareds are the same, plus 144. Do you guys see that? That's exactly what we mean by quadratic form, okay? Same thing here. If we think of this as 2 times x cubed squared minus x cubed plus 9, it's just like we're taking 2 times some variable, and we're squaring that variable, minus that variable again, plus 9. Okay, and so we can then use our quadratic methods to solve these. Okay, so we could use the quadratic formula. We could use completing the square. Or we could solve by factoring. Okay, the only difference is that at the end we're going to need to make an extra substitution. Okay, so let's try to rewrite these in quadratic form if possible. Pause the video, give it a try. All right, hopefully you notice that this is actually not going to be possible. Okay, x to the fourth would be like x squared squared, but then we end up, well, I guess it is kind of possible, it's just not pretty. Maybe I'll rephrase it, it's just not pretty. Not pretty. Right, let me move my writing a little bit down. X squared squared plus 5x to the 1/2 squared plus 6, right? Is x to the 1/2 squared. That power to a power 1/2 times 2 still gives us that degree of 1 that we need. But the problem here is that these are not the same, right? So what if we try x squared squared plus 5 x squared to 1/2 plus 6? Well, now we're in a pinch again because we're not quadratic. So instead of not pretty, it really is just not possible. Okay, not possible. And if you couldn't follow my thinking there, don't worry about it. Okay, just know that it's not possible because we don't have our degrees that are doubled, right? You see that how on these two, 3 times 2 is 6, 2 times 2 is 4. So if our degrees are doubled and we have a trinomial, we can maybe rewrite it. Try this one. So we have this x to the first power minus 9x to the 1/2 power plus 3. So let's just say we want our variable to equal this. Okay, let our other variable u equal x to the 1/2 power. Then we could rewrite this, right? We could think of this as x to the 1/2 squared minus 9 times x to the 1/2 plus 3. Meaning we could end up with u squared minus 9u plus 3. All right, and I'm using the letter u because later in calculus, if you choose to go that route, and in pre-calculus, u substitution is something that happens a lot, and so the equations such as these. Okay, so we're going to try one problem like this to solve, just so that you can say that you've seen one before. Okay, so see, we have our degree, our degrees are 4 and 2. We have a trinomial, so this is an equation in quadratic form. Right, so we're going to use u substitution. We're going to let u equal x squared, that variable there. Okay, and then that's going to allow us to rewrite this as 18 u squared, because this is saying like x squared squared, right? U squared would be then x squared squared, which is x to the fourth, okay, minus 21u plus 3 equals 0. And now I want to ask myself, what method of solving quadratics do I want to try here? I can use a quadratic formula, I can complete the square, or I can factor. Factoring is always my favorite. Some people here would want to just use a quadratic formula. That's fine. But let's try to factor. Okay, so AC method, we want factors of 18 times 3. So factors of 54 that would add up to that negative 21. So we have 1, 54, 2, 27, 3, and 18. And actually, that 3 and 18 pair is looking pretty good, right? We can take negative 3, negative 18. So let's rewrite 18u squared minus 18u minus 3u plus 3 equals 0. And then now we will factor by grouping. Okay, factor out of GCF 18u, you're left with u minus 1. Factor out of negative 3, you're left with u minus 1. Thankfully, these quantities are the same, so we can factor out a u minus 1. Okay, and we're left with 18u minus 3, and then now we can set each of these factors equal to 0. Okay, if u minus 1 equals 0, that means that u equals 1. If 18u minus 3 equals 0, that means that 18u equals 3. So u equals 3 divided by 18, which is also equal to 1/6. But we are not done. Okay, we are not done. Remember, at the very beginning, we made a substitution. So now we have to undo that substitution down here to get our answer back in terms of x. Okay, so u equals this. Okay, remember u is equal to x squared. So we're really saying 1/6 is equal to x squared for both of these. Okay, and now we have to solve out these two equations. Okay, take the square root of both sides, meaning that x is equal to the square root of 1. Remember that we put the we put the square root in the problem, so that creates space for a plus or minus. All right, we're going to take the square root of both sides again. We are putting the radical in the problem, so it creates space for a plus or minus 1/6 to be equal to x. Okay, this 1/6 is a fraction. It is all underneath the radical. I'm okay right now if you just leave it like that. Eventually in the next chapter in Unit 6, I'm going to want you to rationalize that denominator, but for now, this is fine. Okay, and we could also use the quadratic formula here. So only thing that would be different with the quadratic formula, like right here, right, you would say x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, right? You would set up that formula using a, b, and c. Simplify, do all your stuff, and then when you get your values at the end, you just have to work through this idea that we're equal to x squared instead of just x. So you'll still get the same thing. All right, this concept of multiplicity, we have already done this conceptually, so it should not take us very long. Now you just have it in writing. All right, we're going to look at the power of each x when we are solving our equations in factored form. I'm going to write that there, in factored form. That's important, in factored form, to determine their multiplicity. It tells us something about their graphs, right? So if we have a quantity with an even degree, then they bounce, right? So even multiplicity, they do not cross the x-axis, they bounce. Odd, they cross, meaning that they slice. So we've already done this graphically. We're just going to now state the multiplicities. Okay, so if 6x, if we set this entire function actually equal to 0, right, like this, then we end up with 6x equals 0, x minus 9 equals 0, and x plus 7 to the third power equals 0. Okay, and so this means that x is going to equal 0, and then we have to look back at the original degree, which was 1, so it's going to have a multiplicity. I'm okay if you abbreviate it as mult, M-U-L-T, period, multiplicity of 1. Okay, x minus 9 means x equals 9, again with a multiplicity of 1. You're just stating whatever that degree is. Okay, then here we're going to end up with x equals negative 7, and then that degree is a 3, so we're going to have a multiplicity of 3. Okay, and so whatever your multiplicities are added together, they should hopefully be equal to the overall degree of your function. Nothing to get too hung up on, just something to be aware of. Pause the video, give this a try. No, for real, pause the video, try it. It's not going to hurt you. All right, here we get x equals 0, multiplicity 1. 5, multiplicity 1, negative 8, multiplicity 2, negative 9, multiplicity 3. Okay, reading off those, visualizing in my mind, if I set them equal to 0, what would happen? Super easy to do when we're in factored form. Here, this 3 we do not have to worry about. Okay, there is no x with it, so we don't have 0 as an x-intercept here. Okay, but we will have negative 4 with that multiplicity of 3, 7, multiplicity of 2, 4, multiplicity of 1, right? Because that way we have that exponent of 1 out here. Remember that these signs are all going to change because we're setting equal to 0. That's why we have plus 4, but then a negative 4 when we're looking at it, 0. Okay, and then here another same situation with that 8. There's no x with it, so 0 will not be included, but we will have negative 9 with a multiplicity of 2, negative 4 with a multiplicity of 1, negative 5 with a multiplicity of 2. Okay, that's all I got. Try the practice and let me know what your questions are.